Here's problem 14.44. In a game of pool, ball A is moving with velocity v naught I in this direction right here. When it strikes B and C, which are at rest side by side, assuming frictionless surfaces and perfectly elastic impact, conservation of energy in other words, determine the final velocity of each ball, assuming that the path of A for the A part is perfectly centered and that A strikes B and C simultaneously, and then B not perfectly centered, that A strikes B slightly before it strikes C. So the velocity of A is equal to V naught times I. From the symmetry of the situation, we can see that B has got to go off in this direction right here. C has got to go off in this direction. The impulse that's applied to B and C would be identical. So that means the impulse that's applied back to A would be identical. And that means that A would have no change in its momentum in the Y direction. So it's only going to get a change in the X. So we're going to talk about VA prime then. Final velocity is going to be VAX prime in I unit vector. And VB prime is going to be a VB prime in its unit vector in this direction is cosine theta I plus sine theta j, and VC prime would be a cosine theta I minus sine theta j. So this is the vector equation that we have for the three velocities after impact, which is what the prime is indicating. So let's look at conservation of momentum in the Y. And we start off with no momentum in the Y direction at the beginning. And afterwards we have an M VB sine theta right here. And then a minus M VC sine theta, both prime there, of course. And what this implies to us is that that VB prime is going to be equal to VC prime. I'm going to call that equation 1. Let's look at the momentum in the X direction. We start off with an MV naught coming in. We have an MVAX prime in the I, MVB prime cosine theta, and a VC prime cosine theta for the I as well. So out of that, you get the M's canceling out, and you get V naught is equal to VAX prime plus, and since VB prime, VC prime are equal, this reduces down to 2 VB prime cosine theta. I'm going to call that equation 2. I'm going to look at conservation of energy next. 1 half MV naught squared coming in. We have a 1 half MVAX prime squared. We have a 1 half M VB prime squared, and then 2 of those, so that's why I put the 2 out here. So you can see once you clear out the M's and the 1/2 right here, you'd end up with V naught squared equal to VAX prime squared plus 2 VB prime squared. I'm going to call that equation 3. If we substitute VAX prime from equation 2, in other words, solve for that VAX prime in terms of this, and plug it into 3, we'll have V naught squared equal to VAX prime then would be V naught minus 2 VB prime cosine theta, and that's squared, plus then 2 V prime squared, VB prime squared, excuse me. So you get, you square this term right here, you get V naught squared minus a 4 V naught VB prime cosine theta, plus then a 4 VB prime squared cosine squared theta, and then you got your 2 VB prime squared right there. So the solutions you get out of this, the V naught squared go away. You can factor out a VB prime. VB prime, 2 solutions out of that still, VB prime equals 0 is 1. The other one is that VB prime is 0.693 V naught, and it is, as we argued earlier, at the angle of 30 degrees. So if you plug that from 2 then right here, you can find VAX prime then is minus 0.2 V naught in the I, and then the VC prime then and VB prime are equal in magnitude, so you have the same number there, and of course 30-degree angle down. The next part of the problem wants us to find the velocities after impacts taking place if A hits B slightly before it hits C. So we're going to look at the normal direction on B is this direction where theta is at 30 degrees, and then the tangential direction perpendicular to that. We're going to look at that collision alone. So we got M V naught cosine theta for the initial momentum of A in the normal direction. So initial momentum of A is in this direction. Cosine theta puts me the component in the normal direction then. And that's got to be equal to M VA normal prime plus M VB prime and V normal prime. V normal prime is the same thing. So the M's cancel out, leave me a V naught cosine theta equal VA normal prime plus VB prime. If we do our coefficient of restitution equation for this collision, we would have V naught cosine theta before minus the velocity of B before, and that's 0, equal the velocity of B afterwards, which is that, minus the velocity of A afterwards, which is this. If you add these two equations together, you'll see that you get 2VB prime equal to V naught cosine theta, which leads to VB prime equal to V naught cosine theta, and VA prime then is equal to 0. And this makes sense. It's like the pool ball collision you have where two pool balls of equal mass collide head on. One stops and the other one takes off with the velocity the first one had. So this is the velocity that A had in the normal direction. B is going to pick it up. So when you plug in the numbers, you get 0.866 V naught, and B, of course, is at the 30-degree angle. Now, VA tangential from here is going to be a V naught sine theta. VA tangential prime afterwards is going to be the same. And this actually turns out to be the velocity of A that's going into the collision with C. It's just as going in a direction of tangential direction right here, and C is in a normal prime. So I labeled a normal direction and tangential direction for the AB collision, and then I labeled an N prime and a tangential prime here for the AC collision. Okay, and the angles thetas are all marked in through there. You can see them. So we're going to collide A and C next, and the momentum that A brings into the normal prime direction, remember it's only in the tangent, so it's going to have a cosine theta involved there. So the momentum is V naught sine theta, and the component along the normal direction is going to involve cosine theta. So there's your M V naught sine theta cosine theta, and that's got to be equal to M VA normal prime double prime for the second collision for it, plus M VC prime for the first collision for it. So get rid of the M's, and your equation reduces down to this right here. If you do a coefficient of restitution equation with A and C, you'll have the initial normal velocity for A is this right here. The initial for C is 0, and then the final for C is this right here minus the final for A. Again, if you add these two equations together, you'll end up with VC prime equal to V naught sine theta cosine theta, and VA normal prime would be equal to 0. So VC prime, plug in the numbers right there, and you get 0.433 V naught at this angle of 30 degrees. Now, what happens after the collision here along the normal direction is that A loses all of its normal velocity, so it only has tangential. So we got to figure out how much tangential velocity did it have in the first place. Well, it was coming in with a velocity in this direction. So V naught sine theta is the component that is coming in right here, and the velocity it had was V naught sine theta. Sine theta is going to give me the other component, so I'll end up with V naught sine squared theta, which comes out to be 0.25 V naught then, and it's at an angle of 60 degrees and below the negative x-axis.